Hello and welcome. In chapter 2, we spent a lot of time talking about how to find the derivative. Whether we were finding it implicitly or explicitly, we talked about the different rules that we can use to calculate the derivative. What we're going to do in chapter 3 is talk more about how the derivative is useful to us. Why do we care what the derivative is? How can we use that in some context to make our lives easier? So the first thing we're going to talk about in this section is relative extrema and absolute extrema. What they are, how to find them, what they look like from a graph, and how to calculate them using the first derivative test. In this video, we're not going to focus too much about absolute extrema, but in the next video, we're going to wrap up this same section of notes. And in that video, we'll talk about the candidate test and absolute extrema in a little bit more depth. So, what are extrema? Relative extrema are points on a function that have the largest or the smallest y values in a given neighborhood. So these are also called local extrema. You may see that in a textbook. And what we're basically saying is if I have some function, there are different points on the function where there are like little peaks and valleys, and those points are called relative extrema. If we are looking at a point like this, where we have sort of a parabola-looking curve, this would be sort of the top of the hill, and this would be called a relative max, because it is the highest point within that particular portion of the curve, as opposed to looking at something like this piece of the function. This would be called, or this is like a valley, and this could be called a relative minimum because it is the lowest place or the lowest point in that particular area. Now, relative extrema are not necessarily the highest or lowest point on the graph in its entirety, but the highest and lowest point in a particular area or in a particular neighborhood. Something to note, relative extrema cannot occur at an endpoint. So if we had a closed interval, which we're going to talk about in a minute, we can't have a relative extrema here or here because that wouldn't be the highest or lowest point in a given neighborhood because there's nothing happening to the left or to the right of those points. It doesn't look like a hill or a valley. It just looks like an endpoint. Something else to note, we can have multiple relative extrema. We could have 3 relative maxes. We could have 3 relative mins. We could have multiple relative extrema. So let's think about what it is that causes an extrema in a function. So here we're going to sketch a graph with the following criteria. So it says we have a function that is continuous and has a change in behavior from increasing to decreasing at x equals 1. So this function was increasing, and then when it gets to 1, it starts decreasing. And I want you to notice that's creating a relative maximum here. So there is a relative max, in this case, at x equals 1. And why is that happening? Because the slope, right, our derivative, the slope is changing from positive to negative at that particular value. And that's what causes this change. Something else I want you to notice is if the slope is going to change from positive going up to negative going down, at some point that slope needs to be 0. And there's actually, if I drew a tangent line here, the slope at that tangent line to that point, the point which is the extrema, would be 0. For the next one, it says, sketch a function that is continuous and has a change from decreasing to increasing at x equals 1. And again, we have an extrema for the same reason. We're having a change in the behavior of the function. So if it's going from decreasing to increasing, what's happening is that we have a relative minimum. The lowest point on the graph in this neighborhood, a relative minimum. And why do we have a relative minimum? Because the slope is changing from negative to positive. So we're going to formalize this a little bit more in the notes later, but I just want you to see an extrema is caused by a change in behavior. We're going from increasing to decreasing or decreasing to increasing. Let's identify some extrema. So here we have an example problem where we have a graph. I'm going to actually go ahead and identify to the best of my ability what these points are, and then I'm going to have you identify the extrema. So there is the best of my ability of identifying each of those points. So I want you to pause the video and I want you to identify if those points are absolute maxes, absolute mins, or relative max or a relative min, or maybe potentially both. So go ahead and pause the video and then unpause the video and see how you did. So hopefully you have had time to work through this problem. 0, 0 is an endpoint, which means it automatically can't be a relative extrema. A relative extrema cannot occur at an endpoint. It is also not the highest or the lowest of the y values on this graph. So 0, 0 is neither a relative nor an absolute extrema of any sort. 1, negative 10 is both the lowest point on the entire graph that we're looking at, and it is also a relative min because it's making like a little cup shape, a little valley shape here. So it is both a relative and an absolute minimum. The point 440, this is not the highest point on the graph, but it's definitely the highest point in this region. It makes a hill shape, so we would say that that is a relative max. It is the maximum value around in the area or the neighborhood that it's in. 6, 10 down here, this is a relative minimum. It's not the lowest the graph ever goes, but it is a low point. It is a vertex looking point, which makes it a relative minimum. And then last but not least, our absolute maximum is the y value here. There's an absolute maximum at the point 770 because that is the highest that the graph ever goes. So remember, you can have more than one relative extrema, and you can have an extrema that is both a relative and an absolute. Let's keep moving. The extreme value theorem, EVT, says that if we have a continuous function on a closed interval, then no matter what, there's both a max and a min on that interval, an absolute max and min. So think about that. If I had a curve on a closed interval that's continuous, I never lift my pencil. At some point, there's a highest point, which would be here, and at some point, there's a lowest point. Even if we were looking at a horizontal line, the highest and lowest point happen to be the same number, but there still could be an absolute max and an absolute min. That's what the extreme value theorem says. So let's formalize a little further what we've been talking about. We have said that extrema occur at a change in behavior, and we talked about how if we're going from increasing to decreasing, that not only is there a change of behavior causing this extrema, but that the slope of the tangent line would be 0. So one of the ways that something can be an extrema is if the slope of the tangent line at that point is 0, or our derivative at that point is 0. But does that always have to be the case? Can you think of another example of a type of function, one that you've been working with for a long time, that has a relative extrema where the derivative maybe doesn't exist? So I'm hoping that maybe you came up with absolute value. Absolute value has a V-shaped graph, and the derivative doesn't exist at this V-shape, at this vertex point, or at this relative minimum in this case. We would say that the derivative is undefined because there is a sharp turn there. So it is possible that the derivative doesn't exist at a particular point, but that point is still an extrema. So the types of numbers we have just talked about are critical numbers. Critical numbers are one of two things. They are either an x value that makes the derivative equal 0, or they are an x value that makes the derivative undefined. Now, undefined in the derivative, but still defined in the function, because if I have an open circle or something in the function, then this point can't be an extrema because that point doesn't actually exist on the graph. So let's first talk about finding critical numbers, and then let's tie that back to the first derivative test. So we're going to go back to that other slide in just a minute, but let's talk about finding critical numbers first. So here for number 1, I have a function. The first thing I want to make sure is that I'm considering any domain restrictions in this function. So are there any x values that I'm not allowed to plug in? So I'm asking myself, can I plug in negative numbers? Yeah, because I'm taking the cube root. Negative numbers are fine. Can I plug in 0? Yes. Can I plug in positive numbers? Yes, so no domain restrictions. So now I'm going to look for my derivative. I'm going to apply the chain rule. So this is going to be 2/3 times x squared minus 9 to the negative 1/3. And I'm going to multiply that by the derivative of the inside, which is 2x. Now, normally, it's fine to leave things as negative exponents and to leave them unsimplified, but I want to know where this derivative is 0 and where it's undefined. So it's going to be easier for me to multiply these two things together and to put that negative exponent in the denominator so that it's a positive exponent. Because now I want to know two things. I want to know where my derivative is equal to 0, and I want to know where my derivative is undefined. Well, what makes a fraction 0 when the numerator is 0? So the derivative is 0 when 4x is 0, which means the derivative is 0 when x is equal to 0. Similarly, the derivative is undefined when the denominator equals 0. So when 3 times x squared minus 9 to the 1/3 power equals 0, and that would be 0 when this part is 0, so at plus or minus 3. So what we just did was we identified 3 critical numbers. So I'm using Cn to represent critical numbers. The 3 critical numbers that we identified are 0 and positive and negative 3. Let's identify the critical numbers on number 2, and then we're going to come back and talk about how to use these critical numbers, why they're actually important to us. So the first thing that I'm going to notice on number 2 is that x is not allowed to be 0 in the function g, because then I have a vertical asymptote. This function is undefined if x is 0 because the denominator is 0. Now, in order to take the derivative, I could use the quotient rule, or I could rewrite this function. I could split my numerator. I could rewrite this function as 2 pieces, and then I could simplify. That gives me x to the 3rd over 3 plus 1 over x, or x to the negative 1st power. Now, I'm going to take my derivative using the power rule. If I take the derivative here, this 3 is going to drop down in front, and then it's going to divide out. So that's going to give me just x to the 2nd power. If I take the denominator here, this is going to be minus x to the negative 2nd, which is the same thing as 1 over x squared. Now, I want to know where this is 0 and where it's undefined. So this is where this is 0 and where it's undefined. Well, the only place that it's undefined is if x equals 0, but this is not in the domain because we already know that x is not allowed to be 0, so 0 is not going to be a critical number. I don't need this information here. 0 is not a critical number. So now I just need to figure out where it's 0. So I'm going to say 0 equals x squared minus 1 over x. I'm going to add 1 over x to both sides. I want to get all the x's on the same side, so I'm going to multiply both sides by x squared. So 1 equals x to the 4th, which means if I take the 4th root of both sides, x is positive or negative 1. So the critical numbers on number 2 are plus and minus 1. So to find the critical values first, or the critical numbers, first identify any domain restrictions, then find the derivative, set the derivative equal to 0, and figure out where the derivative is undefined. So if we go back to this slide before, we just have done steps 1 and 2. We have found the domain restrictions, we have found the derivative, where the derivative is 0 or undefined, which is called finding our critical numbers. Now, the really cool thing about the first derivative and the first derivative test is that this allows us to find 2 things. It allows us to find the x values of relative extrema, and it allows us to find the intervals on which the original function is increasing and decreasing. And here's how it does that. What we're going to do with the critical numbers that we just found is we're going to place them on a number line, and we're going to mentally plug in values to create a sign chart. And I'm going to show you what I mean on those 2 examples that we just did in just a minute. So we're going to make a number line, and we're going to mentally plug in numbers above, below, and in between the critical values that we found. Then once we have that number line is going to allow us to figure out all this information that we just found here. Anywhere that the first derivative is positive, that means that the function is increasing. Anywhere that the first derivative is negative, that is where the function is decreasing. Anytime we have a change in behavior from positive to negative, so from increasing to decreasing, we have a relative maximum. And anywhere we have a change in behavior on the derivative from negative to positive or from decreasing to increasing, we have a relative minimum. So this sounds like a lot, but let's actually apply it to the two problems that we were just looking at. So on number 1, I'm going to take those critical values that I found and I'm going to make a number line that just contains those 3 numbers. What I want to know is what's happening in the derivative before I get to -3, what's happening in the derivative when I'm between -3 and 0, and what's happening in the derivative between 0 and 3, and what's happening after 3. Because I know that at these 3 values, the derivative is 0 or undefined, which means those are the only 3 places that it could change in its behavior. And notice I said could change. It may not be changing, but it could change its behavior at those 3 values. So I am looking at this equation right here. I am going to mentally say, what happens if I plug in something smaller than -3? What happens if I plug in -4? Now, I don't care what number this simplifies to. I just care if I plug in -4, do I get a positive number or a negative number? So if I plug in -4, the numerator is going to be -16. The denominator, -4 squared is 16. 16 minus 9 is positive. So the top is going to be negative and the bottom is going to be positive. That means that in this interval, we have negative numbers in our derivative. I'm going to pick a friendly number to plug in to this same equation between 0 and -3. So I'm going to think about -1. If I plug -1 in, the numerator is negative, but so is the denominator. -1 squared minus 9, that's going to be a negative number. If I have a negative in both the numerator and the denominator, I have a positive number. Same thing with the interval from 0 to 3. If I plug in something between 0 and 3, like 1, the top is positive, the bottom is negative, so this is negative. If I plug in something bigger than 3, like 4, this is going to be positive, the bottom is going to be positive, so overall the whole fraction is positive. So I'm not showing work, I'm mentally plugging in numbers in each of these little intervals so I can see the behavior of the derivative. Here's the really cool part. Everywhere that we have a plus sign, our original function is increasing because this is saying the slope is positive. That means the original function is increasing. So we can say that it's increasing between -3 and 0 and from 3 to infinity, and we are allowed to say this because f prime of x is positive. We can say that it's decreasing everywhere else, so it's decreasing from -infinity to -3, and from 0 to 3, since f prime of x is negative. So we now know how the original function is behaving everywhere based on the first derivative. The last thing that we can do is we can talk about extrema. So we can say, and I'm going to come down here, we can say that we have a relative, well actually let's look at our number line. From at -3 we're changing from decreasing to increasing. It was going down and now it's going up. At 0 we're going from increasing to decreasing, and at 3 we're going from negative to positive. So you can see we have a relative minimum twice at both positive and -3. And we know this because f prime of x changes its behavior. It changes from negative to positive. That's why we know we have a relative minimum there. We can also say that we have a relative maximum at x equals 0 because at 0, f prime of x is changing from positive to negative. So you can see these little circles or little U's that I'm creating to help me visualize what's happening there. So all of this information is coming from looking at that sign chart. So go ahead and pause the video and get anything you need down from here because I'm going to erase this work so we have enough space to work through number 2. Okay, here we go. We are going to make a sign chart or a number line with the two critical values that we found. I also want to point out that we know that the function doesn't exist at 0. There's a vertical asymptote there, so I'm going to actually add that to my number line, but I'm going to add it as a dotted line. So now I am plugging values into this derivative here to figure out if something is positive or negative. So if I plug in -2, -2 squared is 4 minus something small, that's going to be positive. If I plug in -1/2, -1/2 squared is 1/4, minus 1 over a fraction, so that's going to become an integer, which means this is going to be negative. If I plug in +1/2, the exact same thing is going to happen because I'm squaring those numbers. So similarly, if I plug in +2, I'm still going to get 4 minus 1/2, which is a positive value. So here's my sign chart. The first thing I want to notice is that I have increasing intervals. So we are increasing from -infinity to -1 and from 1 to infinity. And we know this since g prime of x is positive, which you could also write g prime of x is greater than 0. I know that we are decreasing from -1 to 0 and from 0 to 1. So I want you to notice that I did break this function at 0 because 0 is not in the function. I can't say that it's decreasing from -1 to +1 because it doesn't exist. The original function didn't exist when x is equal to 0. So I have to split it there. So this is true because g prime of x is less than 0. We have some relative extrema, so we're going from increasing to decreasing at x equals 1, so we have a relative max at x equals 1 since g prime of x is going from positive to negative, and we have a relative min at x, sorry, that should have been -1. We have a relative min at x equals +1 since g prime is changing from negative to positive. So there was a lot in this section. Let's go back and briefly recap what we covered. The first thing that we talked about is what are extrema. Relative extrema are basically little hills and valleys, little parabola max and mins, if you want to think about it in that way, throughout a function. Relative extrema cannot occur at an endpoint. We talked about how relative extrema actually do occur specifically when we're changing the behavior from increasing to decreasing or decreasing to increasing. Next, we should have talked about absolute extrema. I'm not sure that we did, and I'm going to add that in now. An absolute extrema is the highest or lowest value on a closed interval, meaning it could include the endpoints. I apologize for not talking about that before. An absolute max or absolute min could occur at the endpoints, but it's the highest or lowest, largest or smallest y value for the entire function over that interval. Then we looked at a graph and we identified different types of extrema from the graph. Remember, there can be more than one of any type of extrema. The next thing that we talked about were critical numbers. Critical numbers occur where the first derivative is 0 or where it is undefined, and those values are our possible relative max and mins, the x values. We have to test on a number line by using the first derivative test to see if there is a change in behavior that acknowledges that we do in fact have a relative max or min. That number line also tells us where the function is increasing, because if the first derivative is positive, the function is increasing, and where it's decreasing, because if the first derivative is negative, the function is decreasing. So go ahead and write down any questions that you have, and I look forward to supporting you on this. Thanks for listening.